YouTube player sitting on a roof there. And so we'll see how that develops. Sometimes the quality of the Wi-Fi. Anyway. So where was I? Mathematical models. Okay, they claim to provide a good picture of the truth, and indeed they do, but it can only ever approximate the real world. Okay, because many simplified assumptions are built into mathematical models. But that's okay, because in principle, we know that if we expended enough effort, we could make our models more and more detailed. So there's a vague general way in which, although we're using approximate models to reality, in principle, we could make these models, say, converge to reality. A very loose vague way. So there's a notion of producing approximate answers and, in principle, being able to make those approximate answers better and better. Here's just these aren't exact pictures, but they are suggestive pictures for what we're talking about. So the IPCC, the Intergovernmental Panel on Climate Change, it's a big worldwide organization researching into the climate change and trying to model and predict what the future climate change may be. The FAR, SAR, TAR, and AR4, those refer to the first annual report, the second annual report, third annual report, and annual report number 4, and so on. So it produces a report every year giving an update on its modeling work, trying to predict climate change in the near future. Okay, so this started in 1990, continues. So what we got on the left sequence of pictures down the left-hand side there is a sequence of representations of Europe, North Africa, Greenland, okay, going into Russia, and so on. Okay, it's not an exact precise picture, but it's suggestive. So, of course, we all are familiar with the idea that computing power is becoming increasingly cheaper and more powerful. Back in 1990, the computing power that was available to the IPCC, the scientists working for it, to produce their climate models, that first picture gives you some sense of the level of detail with which Europe, the landmass of Europe, was represented in their weather models, in their climate models. Just some vague blocks to represent the main parts of Europe, the main parts of Greenland. Okay, Britain and Ireland isn't even represented there. It's probably just insignificant in terms of the accuracy at which they were working there. So this is where they're modeling, the way the land mass absorbs the sun's radiation, the way the sea absorbs the sun's radiation, and how that reflects off the interaction. But as computing power became cheaper and more powerful and more accessible, they were able to make their models richer, more detailed. So by the time of the 4th annual report, the level of detail with which the land masses were represented is getting much more recognizable. So you've even got a little separate block for Ireland. Iceland has made an appearance, and so on. Okay. So that gives an illustration of a mathematical model, maybe a pretty poor mathematical model in the beginning, but as time goes by, as computing power becomes more available, this model gets a closer and closer approximation to the truth. The other pictures indicate the model taking account of more and more different effects. So the first one, mid-70s, they were just looking at kind of incoming solar radiation, CO2 being given off from activity on Earth, maybe the effects of rain. But by the 4th annual one, they've got many, many more elements and effects feeding into the model. Okay, we're not going to be investigating the mathematics of climate prediction in this course, but that's just to suggest this notion of convergence and why it might be important. Okay, but in addition, so the models aren't very good, or they can be made better and converge to the truth. But even if you've got a very good model, still, if it's at all complicated, it's anything but the very simplest kind of models. The actual mathematical problems that are set up, the actual equations governing the activity in the model, are too complicated to be able to solve exactly. We'll see many instances where we're tackling problems and we get nice solutions out. Nice, exact, precise solutions with no approximation error or anything like that. Well, in reality, when you're doing actual work, actual modeling work in the real world, that's seldom the case. So even though the models are approximate, the mathematical problems that are set up on them themselves can't be solved exactly. And we have to make do with what are called numerical solutions, secondly. So when we use the word numerical solution or a numerical analysis in mathematics, what we're meaning there is we are using typically computer algorithms to produce approximate answers, approximate values for the future state of the model. Okay, in some senses that's bad. We're only dealing with approximations, but of course it's fine because we can make the approximations very good. And if we invest more and more, usually computing time, into running the models and evaluating the numerical answers, in principle, we can make the solutions better and better approximate the true value, the true future state of the model. So again, we see this concept of convergence. In most cases, we're using numerical analysis to find approximate solutions in a mathematical model, but that's okay, because they're pretty good anyway, and we have the capability to make them better and better, to make them converge to the real solution. And in most cases, we understand how the error terms behave, and in many cases, we can put bounds on the errors. And we know the worst case scenario for the errors. And if we need to control the errors and make them smaller, that can be done. And of course, then we also have the idea that divergence can also be seen at play in the way time-based predictions evolve. So if you think about forecasting the weather, getting away from climate for just forecasting the short-term weather. The weather forecast for Manchester at 6 o'clock this evening is probably fairly accurate. If you look it up and it says, the temperature is going to be whatever, you pretty much believe that the temperature is going to be that value. For 6 o'clock this evening. So we're only looking ahead a few hours. We got fairly good detailed measurements of the state of the atmosphere at the moment, what the evolution in the past week has been. We can pretty easily roll our model forward a few hours to 6 o'clock this evening. But if we look at the weather forecast for 6 o'clock tomorrow evening, you'd have less faith in it. Okay? There'd be a much wider margin of error associated to the predictions for 6 o'clock tomorrow. If you go to the predictions for 6 o'clock on Saturday, you'd be even less faithful. It's probably not worth looking at the weather prediction for 6 o'clock next Wednesday. Probably wouldn't even waste your time doing that, because in all likelihood, whatever the prediction is today, probably going to be quite different within it. So that's a classic case of where you've got a time-based model, and you solve the model, you run the model forward in time, and while you can be sure a pretty good agreement between your predicted solution and the true state for short time periods forward, as you go further and further, whatever errors there are in your solution, they're probably going to explode or get larger and larger as time goes on. Again, you could call that divergence. Okay, so that's kind of in the realm of applied mathematics and engineering, physics, scientific types of things. If we bring it back just into pure mathematics, just into a much safer, cozier world, we get away from the noise of the real world, we just look at our lovely numbers and mathematical objects. Even there, convergence and divergence is essential, a key concept. Okay, we're all familiar, I hope, with to some extent with the integers. Integers are usually represented by the letter Z. Comes from the German word Zahlen, number. Okay, the integers are 0, 1, 2, 3, and so on, the counting numbers and their negative counterparts. there isn't really any large conceptual problem in constructing the integers or defining what they are. Similarly with the rational numbers, which are usually denoted by Q, the rational numbers are represented by all the fractions you can form, one integer divided by another integer. Familiar with that? With the proviso that you can't have the integer 0 in the denominator. But any other ratio of integers represents what we call a rational number. And if you look at the very detailed logical construction of the rational numbers, there aren't any, it's fairly straightforward to construct the rational numbers out of the integers. You do have to do some kind of tidying up because you have this idea that many different fractions represent the same rational number. 1 over 2, 5 over 10, 10 over 20, they all represent a half. But strictly speaking, they're different fractions of integers, but you can kind of group them all together as one rational number. There's a bit of formal construction set here. But that's quite different from the situation where we go, when we widen out our system of numbers to include the irrational numbers. Okay? Now these are, in some sense, perfectly good numbers, things like square root of 2, pi, e, the root of the natural logarithm, and so on. These are all quantities. These could all represent lengths in the real world. They all lie on the same number line that contains the integers and the rational numbers. But they're much more slippier to get a hold of. Okay? You need quite different construction methods to construct the whole system of irrational numbers, the wider system of real numbers, from the more primitive starting blocks of integers. And the key concept in there is the concept of convergence. So one way in which you can capture and rigorously describe irrational numbers is by producing sequences of simpler numbers, rational numbers, that converge to these stranger irrational numbers. Very briefly showed you one instance of that in the induction talk, but this is one example of such a thing. So the number pi, or if you like pi over 4, can be represented as the limiting state of this summation process. So the large sigma there represents a summation. You can see it in simpler terms here. So you're adding up the reciprocals of all the odd integers. So you've got 1, 3, 5, 7, 9, 11, and so on. All the odd integers occurring in the denominators of those reciprocals, 1 over each odd integer. And you're doing this alternating sum. 1 minus the third, plus the fifth, minus the seventh, plus the ninth, minus the 11th, and so on. The minus 1 to the power n plus 1, the middle expression, gives you this alternating sign. It's minus 1 to some power, it's either going to be 1 or minus 1, so each to the power. And then the denominator is 2n minus 1, they give you all the odd numbers. It turns out, it's rather a surprising, perplexing thing, that if you could look at this sum and look at the value that it's converging to, the value that it's converging to is a quarter of pi. But any intermediate state of the sum on the right is a rational number. You took the first 100 fractions given by that summation formula. Add them all up. It is just a regular rational number. Just find a common denominator of all the denominators. It'll probably be a fraction with very large integers on the top and bottom, but it is just a simple, regular, rational number. One of these easy to understand, unproblematic numbers. And this idea produces a sequence of them, this sequence of intermediate sums that gets closer and closer to pi. So it's just one taste of the way convergence is used and the reason it's important, even in pure mathematics. And infinite sequences of mathematical objects. Yes, this is just a summary review. And their convergence, divergence properties are quite important. And we don't just look at sequences of numbers, we can look at sequences of functions, sequences of vectors, sequences of whatever kind of mathematical object you care to mention. This notion of sequences of objects getting closer and closer to some final state, it occurs in many different contexts in mathematics. Okay, so that was just a bit of motivation, a bit of justification for why the study of convergence and divergence is important. So we're going to begin with studying it in the context of sequences and series, and then we'll continue that on and develop it when we look at differential calculus. Okay, at this point I'll pause slightly and I'll just hand out the notes to you. And we may just have, we might have too much time left, we may just have a quick look at maybe an initial definition or two, and then we'll go full steam ahead when I see you tomorrow. And it'd be good if I could maybe have a couple of volunteers. I want to volunteer their strength to help hand out these. You all leaping forward. Thank you, good volunteer there. If you grab a pile and do the left one there, who's going to hand out these? Yeah, just give it free or however many teams around. Yes. Okay. If you could count how many are in each row, this edge person tell me. You got 3, 6, 8. Anybody still need one? Yeah. Okay, thank you for that help. Okay then. So as you can see, so these notes just cover my material for the whole year. You can see there. Oops. You can see the contents there. It covers all the topics that were listed under my name on Moodle. There's a PDF copy of it up on Moodle. So if you don't have the book with you someday and you want access to it, a PDF copy of it. At the end of each chapter, sometimes in the middle of them, you'll find various sets of exercises. There are solutions to most of those exercises at the moment up on Moodle. They're there for the whole book. But I'd encourage you to pretend that those solutions aren't there at the moment. You should really tackle all these problems yourself. First principle is really to get the benefit out of. Because when you find exercises and problems that you can't do at a particular time, that will prompt you to go back and review and revise and check again the concepts that question is referring to, etc. Okay, but the solutions are all there as an extra resource. For use in the tutorials, I do have extra tutorial question sheets which I'll be handing out. I might say, since we haven't talked about sequences yet, I might just give you these tomorrow. So I'll probably have separate tutorial sheets which list extra questions, which will be the focus for the discussion in the tutorials. Okay, well let's maybe spend a couple of minutes just looking at some of the initial definitions. Okay, as I say, the first week getting started, getting introduced. In the first lecture, we won't cover that much, but we'll hit the ground running tomorrow and get to a stage where we can meet some proper problems tomorrow. I'll cut this on the slide. So the material on these slides are just taken straight from the notes. So, sequences. The first chapter is on sequences. Sequences are our simplest type of mathematical object where we can see this concept of convergence happen. Okay. So we're going to study the convergence of sequences. So what is a sequence? A sequence, dead simple. A sequence is just a list. In our case, we'll mostly be studying lists of numbers. But there's nothing stopping you considering sequences of functions, sequences of groups, sequences of vector spaces, sequences of whatever kind of mathematical object. But we're focusing on a nice contained case, sequences of numbers. Okay. Now, when we're talking about these, there's typical notation of these. Okay. So typically, you might see a representation like this. We use subscripts on the letters. We're using x to represent the sequence, and we've got x1, x2, x3, x4. It's just the list of values in the sequence. We're using a subscript to index the elements of the sequence. The dot, dot, dot at the end is suggestive that this thing continues without end. If it did have an end, if it did have a last element, we'd probably just write it in the list. We put a dot, dot, dot in the middle, and then we write down the last element. Okay? But when it's just written like that, it kind of suggests that it's an infinite sequence. So you can either literally list out the elements like that to talk about it, or you can use this more compact notation using these curly braces. So when, in this context, when we see curly braces around a variable with an index letter attached to it, like curly braces xn, we're referring to a sequence. Okay? That's representing the whole sequence. Not any particular element, just the whole list. The whole list itself. Sometimes we can put superscripts and subscripts on the rightmost curly bracket to indicate the starting and ending values of the index. So if you've got an infinity value there, that's telling you that, well, not that the ending value is infinity, but just that the sequence goes on without end. Infinity is not a number like the other numbers. So that's the notation here is telling us that the first element of the sequence is x1. By implication, then x2, x3, and so on, and the sequence goes on without. But we don't always put those in. You know, if it's clear from the context that we're discussing infinite series, normally we could just write curly brackets xn to represent. So let's look at first couple of examples of this kind of thing before we get into talking about convergence. We could talk about the sequence of positive integers themselves. You would maybe give that a defining formula by saying, yeah, we've got a sequence Zn. So we're using n for the index there. And the number Zn is defined to just be simply n itself. So the sequence is really just the sequence of integer indices. It's the most simple sequence we might write down, perhaps 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. And maybe you encountered the Fibonacci sequence before. Typically denoted Fn. The Fibonacci sequence is a sequence of integers, which is interesting as it often arises in patterns, naturally generated patterns, patterns you see in plants and animals. Typically, this sequence arises as signifying some kind of arrangement or symmetry, so parts of the flower or spots on the animal, etc. And this is an example of something called a recurrence relation. So that's how the Fibonacci sequence begins: 1, 1, 2, 3, 5, 8, 13. And the normal, typical rule, definition of it is it's given as you're given a generating recipe, what we call a recurrence relation. So we declare what the first and second elements are. We just say it begins 1, 1. So f1 is 1, f2 is 1. And thereafter, so this is the recurrence relation itself, we give a relation that relates a general element of the sequence, here fn, that relates it in a precise way to previous elements. In the case of the Fibonacci sequence, that relation is that a general element of the sequence is equal to the sum of the previous two elements. So here you have fn equals fn minus 1 plus fn minus 2. So on the right-hand side there, the n minus 1 is the subscript to the first f. The n minus 2 is the subscript or index to the second. If you just check there, you'll see that the numbers given at the start of the sequence, 1, 1, 2, 3, 5, 8, 13, they do indeed satisfy that recurrence relation. And once you know the first two, you can just run the recurrence relation to successively generate all the elements of the sequence. You could write a little computer program to just spit out all the elements of the sequence. Then you've got something like, say, the sequence of odd positive integers. So 1, 3, 5, 7, just every second integer beginning from 1. These are all the odd ones, the ones that are not divisible by 2. We might call that the sequence AN. And here, AN is a nice formula. AN is denoted by 2n minus 1. So when n equals 1, 2n minus 1 will give you 1. And n equals 2, 2 times 2 minus 1 will give you 3. So you've got a nice formula for the nth element of the sequence. Notice it's different from the case in the recurrence relation. The recurrence relation doesn't tell you immediately what fm is, it just tells it to you in terms of the previous element. You have to kind of work your way all the way up to fm, get all the values in order to figure out what the value fm is. But in the case of this formula here, you could just, like if I wanted to know what A100 is, I know straight away it's 2 times 100 minus 1, 199. 100th odd integer. Now, there do exist formulas of this kind for the Fibonacci sequence. That's an interesting exercise to generate the precise form, the direct formula for the nth element of the Fibonacci sequence, just in terms of the index value n. It's a bit complicated, but it's an interesting thing to do. The very important sequence in mathematics, something we'll spend a lot of time discussing in the number theory and cryptography in the second year. Choose to do that. And so these are wonderful numbers, the sequence of prime integers. These are 2, 3, 5, 7, 11, 13, etc. Okay, these are numbers which prime, meaning they're only integer factors, they're only positive integer factors of themselves. 8 is not on that list because 8 can be written as 2 times 4. 10 is not on the list, 10 can be written as 2 times 5. Those numbers, there's no way to write them as a product of simpler numbers, other than just trivially writing 7 as 7 times 1. They're prime numbers. And we usually denote those with the letter P. So we got the sequence of primes, and we actually do know that it's an infinite sequence. When we prove, without too much trouble, that there's actually an infinite number of prime numbers, which is certainly one of the first things we discussed in the second year number theory unit. And does anybody know the formula for the nth prime? Yeah. So there isn't, of the formulae that we saw here, like the nth odd integer is 2n minus 1, the nth Fibonacci number is the sum of the previous two. Nice, simple, direct, easy to work with formulae in a way, but there is no such formula at all for the nth prime. But we know an awful lot about the primes, but there are many things we don't know. In particular, now we have found a lot of the primes using just exhaustive computer search. You look up and find databases of prime numbers, but there is no way to know ahead of time, what the billionth prime number is. The list of ordered prime numbers. What's the billionth prime number? I don't think we've listed them all up to that. Could be wrong, but I don't think we have. But if you give a large enough position in the infinite sequence of prime numbers, nobody knows how to just directly, simply tell you what that prime number is just in terms of its position on the list. They don't behave in any kind of way, which is great for mathematics. You know, if they did behave in a nice, simple way, the story would be over and there wouldn't really be much more to do. The fact that they don't means that there's an awful lot of rich structure and rich problems there to solve. Okay, we better end now. Stick to our schedule. We'll really hit the ground running tomorrow, and we'll get to read some tutorial problems as well.